Hi there, my name is Aharon Haravon. I am a software engineer, and I will talk in this session about autoscaling in Kubernetes. The session is mainly crafted for the people who know already what the pod is, but perhaps are not already autoscaling experts, although there should be some takeaways for everyone. Software should allow business to start small and grow later. Furthermore, at any given time, we want to only pay for the resources that are actually providing us some value. In this talk, we will learn about the autoscaling, the cloud-native applications, and some advantages provided by the open source project KEDA. I will gradually explain the basics, then build on top of that to cover some more advanced topics, and finish with fine-tunings and troubleshooting hints. While the autoscaling beginners will probably learn many things right from the start, the patient experts in the area will get valuable insights towards the lecture end. The service SLA and processing times have direct implications on the autoscaling requirements. Also, autoscaling technology limitations may impose business constraints or limit available cost-saving opportunities. To succeed in designing cost-effective autoscaling solutions, it is crucial to first get familiar with both the underlying technology and your business use case. Horizontal scaling in modern clusters involves interaction of 4 different systems. Each of those software components has its role in making the magic work. We will closely examine the HBA controller and then learn about the KEDA controller. Later on, we will briefly see some important aspects of cluster autoscaler and mention a few points on AWS autoscaling groups. KEDA helps bring the required metrics into the Kubernetes world and creates HBA object. The HBA controller monitors the metrics according to the definition in the HBA object and reacts to the changes in it by removing or adding the pods in an application. Cluster Autoscaler in turn detects nodes that are missing or unneeded and asks the cloud autoscaling infrastructure to adjust the node count. Then, the cloud vendor's autoscaling infrastructure creates new instances that are added to the cluster as additional nodes, or removes them. The source of the metrics for the HBA controller may be from one of the 3 supported APIs: Metrics API, Custom Metrics API, and External Metrics API. None of those APIs is available in Kubernetes by default. To have one or more of those APIs available in the cluster, you will need to provide additional software. Let's note here that while metrics from the Metrics API and Custom Metrics API relate to Kubernetes objects like containers, pods, nodes, ingresses, and such, the metrics in the external API usually relate to external entities, those that live outside of the Kubernetes domain. The Metrics API provides CPU and memory utilization for nodes and pod containers. If your autoscaling strategy is well defined in those terms, then you do not need to use KEDA controller. All you need in that case is the Kubernetes metrics server that implements the Metrics API. In many cases, scaling an application based on CPU or memory is inappropriate. For example, you may want your machines to be fully utilized by each of the workload unit. In those cases, setting the threshold for CPU or memory usage would not be suitable. When your application autoscaling strategy is based on specific metric related to Kubernetes resource, for example, number of requests per second, you may configure your HBA to use Custom Metrics API. One way to add Custom Metrics API support in your cluster is to develop your own custom metric server. The function of this program is to feed the Kubernetes with application-specific custom metric values. The obvious disadvantage of this approach is that we need to create another software component that has to be versioned, maintained, tested, and so on. Also, currently, there cannot be multiple custom metric servers registered in a single Kubernetes cluster. Therefore, you will have to implement querying and serving of all the custom metrics in a cluster from this code. This may turn out to be not feasible and definitely doesn't sound like much fun. Another option is that your application exposes custom metrics on an HTTP endpoint in Open Metrics standard format. This information is then collected by and stored in Prometheus. You also need to install and configure the Prometheus adapter to expose those metrics to Kubernetes so they will be available in Custom Metrics API. The Prometheus adapter configuration is somewhat complex. It requires cooperation between SRE engineer and developers. There is a single Prometheus adapter in a cluster, which is usually the responsibility of the SRE team, and many different applications. Therefore, developers are not independent to set up autoscaling of their service by themselves. Another disadvantage of the custom metrics approach is that the observability stack components, such as Prometheus and Prometheus Adapter, become critical components of your application function. This is where KEDA jumps in. In many cases, your custom application metric is represented as a property of a message broker or by a state of the database or similar. In those cases, KEDA will simplify your application-specific metrics implementation. When applied, your application doesn't need to have to expose metrics for the purpose of autoscaling. It also has simple configuration when compared to Prometheus adapter configuration. Another win is with KEDA is that it will streamline the development process as the developers remain independent in autoscaling implementation. I also like that it leaves Prometheus component outside of the critical execution path. Not that there is something wrong with Prometheus, it just seems like a separation of concerns principle violation in my view. Of course, KEDA then becomes critical part of the critical execution path, but that is somewhat expected, right? KEDA does its magic by out-of-the-box integrations with multitude of brokers, databases, and other middleware systems, and by exposing the information from them in external metrics API, which the Kubernetes HPA controller can work with. Those integrations are called KEDA scalers. So, what about if you are using custom application metrics? Can you still use KEDA? Of course. KEDA comes with a Prometheus scaler. You may use it in combination with Prometheus, avoiding the previously mentioned disadvantages in use of Prometheus adapter. So, after the overview of different metrics APIs and a brief taste of KEDA advantage, it's time to get a look at HPA definition and explain it a bit. The following fields define an HPA: min and max replicas that control the number of pods range within which the HPA controller will grow and shrink the scaled application. Scale target reference pointing to a Kubernetes deployment, a stateful set, or a custom resource being scaled horizontally. Metrics section that enlists the metrics the scaling is based upon, and behavior, which fine-tunes the autoscaling behavior. In this example, the HPA is configured to keep the CPU utilization at 50% on average across all pods containers in all application pods. When using resource metrics for CPU or memory, it is important that your application declare relevant resource requests. The utilization threshold is calculated based on it, so the scaling cannot work without it. Here is another HPA example configured to keep one pod per RabbitMQ message. We can notice that it has all the required fields: min and max replicas, scale target reference, and the metric specification. The metrics array may enlist multiple metrics definition objects. The HPA will set the desired replica number to the greatest value derived from all the enlisted metrics. Metrics type defines what is the kind of the configured metrics. There are 5 types of metrics: container resource and resource types that are used for the metrics API and relate to a container's or a pod's CPU or memory; pods and objects types that are used for custom metrics API originated metrics; and external type for external metrics API. Target type defines the nature of the specified threshold number. For each target type, the HPA controller calculates the required replicas from the metrics value in different ways. There are 3 target types: utilization, expressed as percentage and used exclusively for container resource and resource type metrics; value and average value target type. Let's see how HPA calculates the desired replica count from the metrica value. Generally speaking, the amount of desired replicas in each HPA's evaluation is calculated using this formula. So the number of application replicas will be adjusted according to the ratio of the currently measured metrics and the configured amount in the HPA target section. As usual, the devil is in the details, and the documentation on how HPA calculates the desired number of replicas is rather shallow. Therefore, to look deeper into the matter, you may need to check out the HPA implementation code. Here I'll just point you to 2 files in Kubernetes project that encapsulate the relevant logic. They are both in PKG controller pod autoscaler folder, replica calculator go and horizontal go. As we are focusing on KEDA today, I will present some details on how external metrics-based HPA calculation works. There are 2 supported target types in external metrics API: average value and value type. We use the target type average value when we want HPA to average the observed metrics across the number of total pods, and we use the value target type when the metric is already averaged, so HPA will use it as is. For example, we may use the average value when the metric is queue length, and we may use the value target type when the metric is average time a message spends in queue. Now, let's see how the HPA object behavior affects the desired replicas calculation. Here we can configure the policies for scaling up and down. Stabilization windows declare durations in which the maximal desired value takes precedence over any smaller amounts that subsequent calculation may yield. In the default behavior policy that is shown, all the replicas may be scaled down within 15 seconds. For scale up, we have 2 policies, out of which one yielding maximum amount of pods is applied. The application replicas number may grow either 100% or 4 pods within 15-second window, whichever is larger. We only need to declare behaviors when they differ from this default HPA behavior. The HPA controller runs inside the process called Kube Controller Manager. along with many other Kubernetes controllers. To fine-tune the global HPA parameters, we need to change the command line arguments sent to the kube controller manager at the start time. Here is a small selection of important global HPA parameters. The HPA sync period defines the polling period of the metrics. Its default is 15 seconds, and you may want to reduce it for greater responsiveness. The downscale stabilization with the default of 5 minutes sets the time window in the past from which the scale down recommendation maximum is selected. The tolerance sets the metric change sensitivity threshold. If you have many HPA objects, you may want to increase the concurrent horizontal pod autoscaler syncs to ensure more responsive reactions. For CPU-based scaling, make sure you understand well the CPU initialization period and initial readiness delay settings, as they both delay the inclusion of a ready pod into autoscaling considerations. When using KEDA, we declare scaled object CRD, which in turn automatically creates an HPA object for us and exposes the metrics from the external system of our choice in the external metrics API. The following KEDA object specification is all we need to add to our application in order to have it autoscaled based on RevitMQ queue length. In addition to the fields that we already mentioned from the HPA object, namely min and max replicas and scale target reference, we declare here several more. The main one is the trigger section, where we enlist one or more metrics definitions based on large choice of supported middleware systems. The trigger definitions largely vary depending on the scaler of our choice. The default metric target type in KEDA is average value, but you may declare a trigger or with a target type value by adding metric type field to the trigger definition. KEDA also performs the scale down to 0 if min replica count here is set to 0. In that case, cooldown period defines how long to wait before scaling down to 0. The polling interval sets a period for KEDA's polling of the external metrics. Alright, now we've covered the three types of metrics API. We've seen why KEDA and external metrics API is the way to go. We also learned about the fields of the HPA object and KEDA scaled object, and we explained how HPA calculations work for both average and value target types. Now we shall see a bit about the cluster autoscaler function and mention a few of its parameters that we should be aware of when tuning the solution. The cluster autoscaler detects that a pod cannot be scheduled due to a resource constraint, such as insufficient CPU or memory, or due to other constraints, such as affinity and anti-affinity. In turn, it communicates with the cloud provider Autoscaling API to demand a new node. Likewise, when a node's resources are free beyond a configured threshold, the cluster autoscaler releases the node. This list enumerates some of the important cluster autoscaler parameters you should consider when troubleshooting or fine-tuning your autoscaling setup. Scan interval sets the frequency of scale-up or down evaluations. It defaults to 10 seconds and should be reduced for quicker reactions to changes in workload amount. Scale-down delay after add defines how long to wait after a scale-up before scaling down any nodes. The default 10 minutes can be reduced to 10 seconds or so to minimize the costs. The scale-down unneeded time controls for how long a node should be unneeded. like below the usage threshold before it's taken out, which defaults to 10 minutes and also can be shortened. The scale-down utilization threshold defines the unneeded node threshold as a percentage of usage, with the default being 50%. Make sure to adjust those and other cluster autoscaler parameters in order to get a smooth autoscaling that best suits your needs. When cluster autoscaler scales the Kubernetes cluster, it talks with the cloud vendor autoscaling API. In AWS, it is called AWS Autoscaling Groups, or AWS ASG. The AWS ASG has advanced autoscaling capabilities of its own, like scaling policies, scheduled scaling, or predictive autoscaling. But when used with cluster autoscaler, it operates in so-called manual mode, as cluster autoscaler makes all the scaling decisions. Provisioning a cloud virtual machine instance is not an instant operation. It takes some time to create and boot the machine, then the machine needs to be bootstrapped with Kubernetes installation and configuration. To reduce the time required to add a node to the Kubernetes cluster in AWS, we may use the AWS ASG wormpool feature. When applied, the AWS ASG prepares the configured amount of nodes by pre-launching them and running the launch template scripts that perform the installations. Then the wormpool instances are shut down. You only pay for the instance root volume disks during the time the instances are shut down. This way, you enjoy faster node startups and therefore faster scale-out of your cluster, meaning a more responsive and cost-effective service. Make sure to test your autoscaling setup. When testing it, you may want to simulate load peaks and monitor timings of different stages of pods, EC2 instance, and Kubernetes node initializations. This list shows the events in their common chronological order. When using regular instance groups and default parameters for all the system components, you may expect to get results similar to ones in this chart. The pods are created between the first 0 to 50 seconds and become ready in some 140 to 250 seconds. In my use case, this was not good enough, so I went on and fine-tuned some parameters. I started with configuring the HPA behavior by allowing more than just 4 nodes to scale up at once. This already drastically improved the results, but still it wasn't enough for my use case. I needed to have pods ready within 60 seconds to avoid keeping so-called headroom nodes without any load serving as a buffer for a spike in workload demand. So I went on to set up wormpools with pre-pooling the container images at the launch template scripts, and I got this result. Pods are now ready within 40 to 60 seconds since the need for them is detected. In my case, this meant significant savings for the company, as no expensive resources need to be kept, only to be able to handle spikes in workloads. I hope these hints inspire you to test and fine-tune your system autoscaling parameters. It is worth noting in this context that to ensure the high availability of a cloud-native app during the autoscaling process, we need to configure the affinity, pod topology spread constraints, and pod disruption budgets. For example, if we forget to set the affinity, we may end up running multiple pods on the same service on the same Kubernetes node, and therefore have a non-reliable single point of failure, as well as prevent the detection of the need to scale out. There are many additional aspects of Kubernetes that are related to horizontal pod autoscaling and were not explained or even mentioned in this session. For example, pod priority and preemption effects, pod volume effects, different available cluster autoscalers like Carpenter and commercial ones, and so on. Equipped with the information from this session, you can easily further enlarge your knowledge and build some cool stuff with it. To help you try it all out easily, I've created a GitHub repo with Terraform and kops files to create a Kubernetes cluster from scratch in an AWS account. There are also two Python apps, a web UI to submit workload, and RabbitMQ consumer service that emulates heavy data processing. Also, there are scripts to export the data required for the charts I presented here, so you can easily reproduce them and tweak for your own use case. So here we have a short mention of the used graphic sources. So thank you for your attention. You can reach me at the email address shown here. Make sure to subscribe to my channel